Okay, so we're going to start with chapter 14, and I've been going over this so many times. What I'm going to do right now, I won't tell any extra stories. Okay, this chapter is about chemical kinetics. Kinetics talks about the rate, and the rate is another term for the speed of the reaction. It's important in chemistry for us to know what chemical kinetics is. We're told here it's the study of the factors that affect the rate of chemical reactions, such as temperature. Temperature is one of the many factors that influences the rate of the reaction. We're told the rate of the reaction is a measure of how fast a reaction makes products or uses reactants. There are two main ways you can figure out or calculate the rate of the reaction. You can figure out how fast the reaction makes products, and you can use that to figure out the rate of the reaction, or you can figure out how fast the reaction uses up reactants, and you can use that value to figure out the rate of the reaction. Either one will give you the same rate as long as the reaction is the same. Okay? It's important for us to have the ability to control the speed of the chemical reaction. That is important. Sometimes the manufacturer wants the reaction to be done quickly because time is of the essence. For example, at some point in the synthesis of the vaccination, there was a chemical process. So if time is of the essence, like people really need that vaccination, they will make sure that they're doing the chemical reactions speedily, right? Fast. So you want to know what factors can influence the reaction to make sure you get the reaction fast or the product fast, right? Sometimes the quality of the product matters, and in that case, you want to make sure the reaction goes slow, takes its time so you can get a good quality product. In that case, you want to know what you can do to slow down the reaction to influence the quality of the reaction. So what we're looking at here is what makes the reaction go fast, what makes it go slow. We're not judging the quality of the reactant. Sadly, in this chapter here, we won't look at that. But those of you going off to organic chemistry, you will get to judge the quality of the reactant based on the condition of the reaction. So if you're going over to organic chemistry, make sure you really understand this chapter. You will need it in organic, okay? Because it most likely will not be covered again. Okay. Besides learning about how to make a reaction fast or slow it down, the next thing we're going to be looking at is the factors that influence the reaction, which have to do with reaction mechanism. So reaction mechanism influences the chemical reaction. So we're going to be learning the reaction mechanism, which is play by play of the reaction, the different steps. So even though we think reactions occur in one step, we will learn that the reality is even the quote-unquote one-step reactions occur in many steps.
Okay,
so as we look at those
I
many
am
step
starting
reactions, the
this
reaction mechanism,
session
we
right
can
now. This
see
is my
which
eighth
part to
take.
tweak
Hopefully this
to
works out.
influence the
In the last
overall
one, I
rate
got
of
a
the
call from the
reaction.
school
So
saying
hopefully
there
you
was no
get the
classes until
gist of
next
it.
week,
We
and
are trying to
that
make
got
the reaction
recorded. No, I
go
did not.
faster.
I had to
For the most part,
redo
our
the
goal
tape.
is
Anyway,
speed,
we are
right?
looking at chemical
So let
kinetics.
me start
Remember
here
the
with this
chapter
slide,
chapter
looking at
14.
factors
I'm going to
that
go
in
straight into
general
it because I think,
affect the
yeah,
rate
I'm
of
just
the
going to go straight
reaction.
into
So
it
for the
before
most
something else
part,
goes wrong.
what we are
So
learning
right
is the
now,
general
let me make sure
trend
I am
and the
recording
general
though, so
expectation
that
or
we don't have an
observations. Now,
issue
with
there. I am
chemistry,
recording,
even
and
though
then
we
let
are
me make
going
sure
through
my audio can be
generalizing, that's
heard
kind
because
of
that
like
was the issue
stereotyping,
before.
right? And
I am
stereotypes
recording and my
occur
audio
most
can
of
be
the time
heard.
with the
Okay.
chemicals, but you have the
So
chemicals
we're going straight
that
into
do
the
not
lesson.
obey the stereotype or
Chemical kinetics
generalization.
is
So
the
you want to
study
be
of the
aware of that.
factors that
Just
affect the
because
rate
we're
of
learning
chemical
it doesn't
reactions,
mean that
such
the
as
chemical
temperature.
will
We will
fall
see later
in
on
that
there's more than just
category.
one factor,
Okay.
but for right
So
now we're
number one,
saying there are
generally,
certain
most of the time,
characteristics
not
that
100%,
influence the rate of the
the greater
chemical
the
reaction.
concentration of the
Once we know those
reactant molecules,
characteristics, then we
the
can
faster the
use
reaction.
them
So
to
for
our
most chemical
advantage. Okay?
reaction, the
When
rate
you
of the
go into the
reaction
chemical
is a measure
reaction
of
or
how
you go into
fast
the
the
lab to do
reaction
the
makes products
experiments,
or
you
can
uses
have this
reactants.
expectation.
So
Okay,
we'll
this
start this
hypothesis
chapter by
based on
looking at
experience
both
that if you
making
increase
products.
the
The
concentration
chemical
of the
reaction we
reactant,
have,
it
how
will make the
fast is that
reaction go
making
fast.
products? or
But
how
since the
fast
term
is it using
generally is
reactant.
used
We'll use
here,
both
that
products
means
being made
about
and
98% being
98%,
used
maybe
to
90, I
measure
don't know,
the
maybe
rate of the
85. It
reaction.
doesn't mean
Towards
all
the
the
end of
time. It
this
just
chapter,
means
we will
most of the
focus
time.
on the
Okay.
reactants only
When we're
because it
looking
makes
at
it a lot easier to focus on
concentration
just
goes
one thing.
with
But we are being told in
solutions
the beginning,
or
you can
liquids.
focus on
But
either
if you're
the
dealing with the
reactants
gas, since
being
gases don't
used
really
or the
have
products being made.
concentrations, for
Okay,
gases in the
the
place of
ability to control
concentration,
the
we'll
speed of the
deal with
chemical
pressure.
reaction is very
The higher
important.
pressure
Okay,
goes with
ultimately,
gas,
sometimes we want the
right? So
chemical
for
reaction
gas,
to
we'll
occur
say higher
faster.
pressure,
If that's
while
our
for
goal, we want to
solutions,
know
we'll
how
say
to
higher
influence the
concentration.
speed of the reaction
Okay, we're told here,
without damaging or
increasing
stopping the
temperature
reaction.
increases the
So
reaction
besides
rate
studying
for
about the
most
speed, we're going
reactions.
to be
Now
looking
we
at
have that
the
term, right?
reaction
So I'm
mechanism.
highlighting those
So I'm going to go ahead and
important
go
terms they
straight to the
use in
factors affecting
chemistry,
the rate of the
kind of
reaction.
like a
We're told,
uh,
number one,
cover me
generally,
term,
that
right?
means let's
As they
say
use this
90 to
generally.
95%
That
of
way,
the time,
when you face the exception and you
the
go back and
greater
say,
the
wait a minute, I thought
concentration
you
of the
said all the
reactant
time. They'll say,
molecules,
no,
the
we
faster the
said
reaction.
generally. That means
Later
most
on,
of
we'll
the time,
talk about the
but not all
collision
the
theory.
time. Collision
And this
theory
term
is a
here,
theory
most
that talks
same
about
idea. Chemical
for
reactions
most
from a
reactions, when
fundamental
you increase the
point of view.
temperature, the reaction
Okay.
goes faster. That means there's
So
some
when we're
reactions
looking at
for which
this,
this is not true. And
we're
then we're
told
told
here,
here,
in general,
increasing the
if
surface
the
area causes an
concentration
increase in the rate of the
increases,
reaction.
the
This
reaction
happens
goes
often,
faster.
right?
Okay.
If you increase the surface
So
area, now
if
the
you're looking at the
chemicals don't
concentration, for
have
the
to
most
go
part, the higher the
from a
concentration,
chunk.
the higher the
As far
reaction.
as the chemical
Concentration
is
is a term
concerned,
that's used to
most of
describe
the particle sizes
solutions.
decrease, so the reaction, there's more
And then pressure is a
contact
term
for
that's
the
used to
reaction to take
describe
place.
gases.
Contact is important in a
Okay.
chemical
Give me
reaction. We'll
just a
see that all
moment
later on in the
right
context
here.
of collision theory
Hold
and the
on.
chemical reaction. Okay. Number 4, what about the physical state? We're told here, in general, gases tend to react faster than solids.
And of course,
I'm
then
responding to an
liquids.
email
Now the
real quick.
order
Give
is
me just a
solids
moment. Will tend to react slowly compared to liquids. Liquids are slower. Liquids and solids are slower than gases. Gases tend to react the most. And we'll see down the road looking at collision theory, because gas molecules are very energetic. And gas molecules will act like they have a higher temperature, being more
that I had to
energetic.
respond to
They're
that
able to
immediately.
move
So I
around
do
more
apologize
and
for
meet
that.
with the reacting
Okay.
molecule
So we
to
do
make the
have
reaction go faster.
increasing
Versus solid
temperature
molecules
increases the
are
reaction rate for
sedentary.
most
They're
reactions. So in
bound
this
in
case here,
place due to the
if you
strong
increase the temperature,
intermolecular
the
forces.
molecules move
So
around
it's going to be
faster.
a
They can
while
find
before
each
they get up
other,
and move around
and then the
find their
reaction
partner
rate
to
goes
react
faster.
with.
So once
Right?
again, we'll
Well, I
talk
just
about all
realized
these
something.
factors down the road.
I think I'm probably more
And then
comfortable
we'll
in
start
this
we'll
phase
try
because
to
I
relate
had
that
this
to the
screen
collision
a
theory.
lot bigger
Okay.
before, and
If
then
you
I was
increase
making a
the
lot of
surface
mistakes. So I'll
area, it
just leave
causes
it
an increase in
like
the rate of the
this.
reaction.
Okay,
The
and
surface
then we
area being
have
increased causes a greater
catalysts.
exposure,
Now, what
right? So here we're
catalysts do
talking about the
here is, for
exposure
the
of the
most part,
molecules.
with the catalyst,
When the
we
molecules
tend
are
to
more
use
exposed,
catalysts.
they
Let me
can
make sure this
actually
recording is
find each
on.
other. Not really see, they
Because
don't have
sometimes I
eyes, but
forget
they
to
can
spell.
find
Yep,
each
it's
other,
recording. I
collide with
forget to
each
press
other,
that,
and
and then I
therefore
go through the
react.
whole
For the
lesson. I realize,
molecules to
oh,
react,
it's
they
not
have to
recording.
be in
Okay,
contact with each other.
catalysts tend
They
to
have to
speed up
find
the
each other. They have to
reaction by
come close, and
changing
then
the
they have to
mechanism
react.
of the reaction.
So when we're
That's why
comparing
we study
gases,
about
liquids, and
catalysts
solids,
after studying
with
the
the
mechanism,
gases, what
right?
we see
Once
is
you know the
gases move
mechanism, then
faster.
you
So when
know
the
which
gases move
part needs
faster,
help.
once again, they find each other
Not the whole
quicker,
reaction
and that
needs
makes
help.
the
There's so many
reaction
steps
go
in the
fast.
chemical reaction.
Versus
Maybe the small
solid
part, maybe
molecules,
one
they're
small part needs
sedentary.
help. So as a
So stuff will
scientist,
have to happen
you get to
before these
select your
molecules
catalyst
actually find
based on
each
the
other
reaction
and
type,
therefore react
and
with
you
each
know which
other.
part of
The
the
reaction
reaction
will
needs
happen with
help.
solids. It will just take
Okay, so we're
longer
moving
because we'll
on
be
to
waiting for the
defining rates.
molecules to
Okay,
find each other.
this chapter,
Okay.
I'm going to give you a
Catalysts,
caveat right
they're
now. I'm
able
going to
to
be
speed up
like
the
chemists
chemical
and give you a
reaction by
caveat.
altering the
This
mechanism.
chapter
So
by
we'll
some
study about
people is
catalysts towards the
tedious
end
after
because they
we
get
have
lost in
talked
the
about the
details. So at
different
some point, I'll
mechanisms
give you guys a
available.
summary
Okay, of how we define
so now we're
rates,
talking
because
about
there isn't
defining
one
rate.
way to
Exactly
calculate
how
rate.
do we
There's so many
define
different
rate?
ways. So I'm going to be summarizing
Well,
a
we're
lot so that
told
you can
here
just
rate is
remember the take
how
home
much a
lesson
quantity. Now
if
the
worse
quantity
comes
here
to
will
worse.
be
Okay,
either
so rate is how
amounts
much a
of
quantity
chemical,
is
right?
changing over a
Amount
given
of
period of time. This is a
reactant
generic term for rate before we bring it into
or
chemistry, right?
product.
a quantity
So at this point, you're trying
changing
to find
over a
how much
period
the
of
amount
time.
of reactant or
Okay, the
product
rate of a
is
chemical reaction
changing
is
over
measured
a
in
given
terms of
period of
how
time.
much
So
the
in general, we're
concentration of
told
the
here
reactant
the rate
decreases,
of a chemical
or
reaction
the
is
product
measured in
increases
terms
in
of
a
how
given
much the
time. So we're told
concentration
here
of a
essentially,
reactant
okay,
decreases,
let's
or
summarize
the
the second
product
paragraph because
concentration
this one here
increases
has
in
to
a
do with
given
chemistry.
period of
We can
time.
get to the
So
same
I'm
rate. So I'm
starting
going to use the
with the
term rate to
definition, this first
refer
one
to
here. Let me
rate.
highlight it.
They
By
change
studying the
this. I'm trying to get
change
used to
in
them.
concentration
In the first one, we're
of the
told the
reactant
chemical reaction rate, or the rate of the chemical reaction,
over
is
change
measured in
in
terms of
time.
how
I'm pretty
much
much
the
going back and
concentration
looking
of
at
the
what's written here,
reactant
right?
decreases. So I'm
So
spending
here we're
some time down
told
here
a
using this
chemical, the
equation
rate
to
of a
see
chemical
how I have
reaction is
accounted
measured in
for
terms of
the
how much
information
the
specified in that
concentration of the
definition.
reactant
Okay, we're trying to find rate of the decreases.
reaction,
Okay,
right? So
usually
that's this right
to
here.
refer
In
to
terms of the
decrease or
reactant
to give
concentration,
account to
I have the
decrease, I'm
term
going to use
reactant
the
here to
negative here.
refer to.
Okay,
This is just
negative
communicates to
here just
you. I
means
am monitoring the
amount
reactant only, right? In this equation, I can solve for the rate of the
decreases
reaction, and in this case,
with
I'm monitoring what
time.
chemical? The
Okay,
reactant only.
they
It says
did
so right here.
say the
What
concentration
amount
of
of
the
the reactant
is
or yeah,
decreasing.
the
So I
reactant
put
is
the
measured
negative
in
there to say the
concentration, right? How
reactant
do I
is
know that?
decreasing.
From the bracket?
Okay, bracket
You can also
symbolizes
figure out the rate
concentration.
by
That's the
studying the
symbol that's
product.
used
We
to
can look
communicate
at the
concentration. So when
the
I'm looking at the
change
reactant amounts, I'm looking at
in
the
the
reactant
product
concentration.
concentration
Okay, so what is happening to this reactant
divided by
concentration? Well,
change in
it is
time or
changing
per change
according
in
to the
time.
definition,
Here
right?
we're
Well,
told
how is it
for
changing?
the
It's
product
decreasing.
concentration increases.
So
So the
in this
product is actually
one
increasing
equation, a
because it's
lot of stuff
increasing.
is being
I can put
communicated,
a
right?
positive
It
in
is
the front
decreasing,
if I want,
and it's
or I can
decreasing
just leave
according
it
to
as
what?
is
Since
since the
change in
positive is
time.
implied.
So this
Okay,
equation
so
communicates
both
the
rates of these
definition
are the
of the
same.
rate of the
Let me go ahead and
reaction when we're
add a
tracking the
term here.
reactant.
Okay.
Or add a
Remember, we
page
figure out the
because
rate by monitoring the change in
I feel like I'm running
concentration
out of
of the
room.
reactant
Oh, come
with
on, add a
time.
page.
Okay. So this is where I
Add a
stopped before,
page.
because right when I
Okay.
got here,
So they're
my
both
phone
rates.
rang, and I have an iPhone and I'm working on my
Rate
iPad. So then my iPad rang and it became a
equal
huge distraction.
this first
Anyway,
one here.
I can
Let me
figure
see if I
out
can
the
just
rate of
be
the reaction by
not
looking
super
at the
lazy, but a little
reactant.
lazy. What happened to
But if
my
I don't want to look at the reactant, I can figure out
something
the
changed?
same
What's
value,
that?
the rate
That used to be the scissors.
of
It changed. Okay.
reaction by
Anyway.
looking at my product. If my
So
focus
yeah,
is my
rate is
product,
equal to
once
that,
again, I
or the
have to
other
look at the
rate as I
change
drew
in
it
what? The
is equal
concentration
to
of the chemical
change
type, which
in
is the
product
product, over
concentration
change in
over
time. So as
change in
time
time.
changes, how does the concentration
And
of
I
my
say
product
here
respond to that changing in
amount
time? Okay, let's try to make sure that this matches the
increases.
definition they said right here. I'll use a different color,
Okay.
green. Remember,
Or
the
these are
product
equal to
concentration
each other.
increases. This time it's increasing
Equal
in the given period of time.
to
So I have
each
to make sure it's
other.
increasing.
Okay.
Now you can put a positive
So if you're
here
either
to
tracking the
imply
reactant
it
or the product, you
increases,
should get the same amount,
or what chemists
which is
do,
the same value
the
of rate.
positive is implied, so they leave it
So
out.
the
Okay,
other
but
thing
the
I want to
negative is never
mention here
implied, so it
is
has to be written,
rate
right? So
is
here we're being told for the same
always
value, rate of the reaction, you can figure this out by monitoring the
positive. Okay.
change in
If you've
the
had physics, some
concentration
parts of this chapter may
of
be a little
the
bit
product
confusing because
as
they use the
time
term rate in
changes.
physics also.
Okay,
If they
so
didn't
this
use
is
it,
the
then it won't be
generic
confusing. If they
formula. You
did,
want to
it
make sure you
might
know
be
the
a little bit
general
confusing.
formula
But let's
because
look
it
at the
comes up
context
later
and
on.
why this
If
is
your
true.
minor is
In
chemistry
the
and you plan
chemical
on taking
reaction,
upper level
we are looking
chemistry,
at
junior
how
level
fast the
chemistry, you will
chemical
see all of this
reaction
14,
is.
12
We're not
again
the
in a
chemical
class
reaction
called,
never decelerates. Even if the
that's
reaction
all
is
I would say,
slower,
physical
it's still
chemistry.
proceeding. So the rate can be
It
big
has some calculus
to
in there,
mean
it
that the
has some
reaction is
physics in
going
there, and it has some
faster,
chemistry
or
in
the
there.
rate can be small to mean the reaction is
Hmm.
going slow.
That's
But
all
the
I'll say
rate
for
is
right now.
never negative.
Like I
Okay.
mentioned
So I'm
earlier,
saying
guys,
here rate is
we
positive.
are going to be tracking
If
our
rate
reaction. Now,
is
we don't get to make a
large,
judgment here. The judgment got made for us. So we're going to
i.e.
confirm the judgment. Do we agree or
reaction
do we not agree with it? Obviously, we agree
is
with it because it's a
fast.
textbook, right? The author wrote it, but
If
let's see why
rate
this is true.
is
Why is this
small,
labeled a
this
reaction with a
means
fast rate? I would recommend to you guys, if
I'm
you see a
being
question like
lazy.
this,
But
the
yeah,
response from you
reaction
should be
to
is
track. You're
slow.
tracking, right? Track the changes
Okay,
from one
so a
box to another. You're
small
trying to
rate
see what
value
kind of
just means the
changes are
reaction
happening.
so
Is
when you
slow,
see this, your
not a
first response
negative
is
rate
count.
value. So in chemistry,
Count
the rate is always
particles
positive. It's never negative.
to
Okay.
determine
In physics, if a body is moving
transformation.
forward and its
So what I'm
acceleration is
going to try to do
increasing,
right here,
it can
y'all, is
decelerate.
count. So I'm going
And
to try
here
to
there is
talk about
no
what I'm counting
deceleration as
so
far
I
as
can be
the
counting the
reaction is
same thing,
concerned. So we
right?
have a fast rate
Okay, I'm
and
going
we
to
have
start by
a
counting
slow rate.
A.
Okay, big rate, small rate. So
And then I'll
hopefully
do
that kind
B
of
and C
helps.
at the same time so I don't get confused. I'm
If you
counting
were
A.
ever confused into the
Okay,
two. If
A
you weren't, don't
is
even worry
this
about it.
circle here. Well, it's not really a
So
circle,
let's
sorry.
go
A
ahead
is like
and
it's like
practice what
a
I just said, what I
capsule
just
and it's
mentioned right here.
bluish.
We're gonna
It
be
looks blue
looking
from
at
where I'm sitting.
the rate, the
And
reaction
then B
rate,
is a
okay?
circle and it
So
looks
total
red.
here,
And then
this one on
C
the left, the
is
picture on the left, which pretty much goes from top to
oblong
bottom,
and it
is
looks
a
green.
reaction with a
Okay,
fast
so I'm
rate.
gonna
So
go
the
through and
judgment has
count
already
A,
been
B,
made
C.
for
Somehow somebody
every
looked at this
given
and
time.
decided
This is the
this
fast
is
rate.
considered the
All we're
beginning
gonna do
of
is
the
confirm what
reaction
they have
before
said.
anything
So
reacted. So
the
over here, I'm
reaction
gonna
has
start
not
here.
taken place
This
yet,
reaction
right?
has the
In the
fast
lab, we
rate. That
tend to
means
start the timer
the
when we're
rate at
ready for
which
the
the
reaction to
reaction,
take place,
either the
not
reactants are
before.
being
So right
consumed
before the
or the
chemical
products are
reaction
being
takes
made,
place, it's fast.
our
So what I'm
time
gonna do
is equal to
here,
0 seconds.
let me actually,
How many
I,
A's
I'm
do
going
we
to get
have?
used
By
to
the
this
way,
new
at 0
icon
seconds, we
here.
tend to have the maximum amount of the reactants. So go 1, 2, 3, 4, 5, 6,
Hold
7,
on.
8. We got 8 amounts of A.
No, come
How many
on.
amounts of B do we have? Okay,
1,
let me make
2,
this a little
3, 4,
smaller.
5, 6, 7,
8. 8 amounts of B.
There used to be
Okay.
scissors.
How
They
many
just
amounts
changed.
of
It must
C
have
do
just
we have?
updated.
How many products do we
Okay,
have in the
so I'm
beginning?
gonna copy that
None,
and put that right
because the
here, and we're gonna
reactants
be
have
looking
not
at the
reacted
rate
yet
to make a
as
product. So
far
we
as
have
the
0.
reactant is
No products,
concerned,
no babies, no kids, right? Then with time, the reactants react. How much time has passed? By the way,
okay?
since these
And do the
increments
same
are
thing
huge, I'm
and
gonna
look
estimate
at
the time based on
the
what I
rate,
think it is,
for this
right?
part here.
So I think
The
it's
second one, we're going to be
around
studying
20-ish.
the product.
We're gonna be happy with that. We're okay with that, right?
Okay.
20-ish, 20 seconds. Okay. At 20 seconds, 20
And I'll be
seconds
looking
have
at this
passed.
down here.
Remember,
Paste image.
reactants. I'm gonna write on the side
Okay.
here.
So with this
Reactants
first one here,
decrease with
okay,
time because they're being
Come on.
consumed, right? And then what happened to products? The opposite. They're being made. Products increase with
okay, I'm trying to get
time.
used to this. Okay.
So the idea here, as we're
This thing
examining this,
has-
is we're approaching this from the
They change the
scientific point of view, which is
sensitivity,
you
so-
approach things with hypotheses,
I'm selecting it, but it's not responding
prejudgments.
to.
But you remember that your
on.
hypotheses are subject to
Come
change if your data tells you otherwise, right? So we are approaching this knowing, okay, reactants are supposed to decrease as time goes by.
Okay, let me see if I can just increase
Products
this
are
from
supposed
here.
to increase as time goes by.
Maybe it's my pencil.
Let's see what's
Something
happening,
is happening
right?
to where it's not
So 20
responding
seconds
to
have
the
passed.
pencil.
Okay, our
Okay,
reactants,
hold
starting
on.
with the blue ones, right? 1, 2, 3, 4. Oh, look, we only have 4
Come
left. Now I'm
on.
only counting what is left, not what has reacted, right? There's only 4 left. And then the red, 1, 2, 3, 4. There's only 4 left. So if 4 of
Okay.
A, I can say here,
Yeah, this is such a huge
4 reactants.
problem for me right now. Okay, let me just go ahead and do the first part because this
Reacted.
is just a distraction. Okay,
Right?
so what I'm going
4
to do
of
here is
both
I'm going to track
reactants
A,
reacted.
B,
It just
and
so
C.
happens that the
One of the
amount
things I
that
want you guys to learn how to
reacted
do
is
is when you're
equal
given a
to the
picture like
amount
this,
that
you
is
want to know
left.
how
But
to
when
handle
they're
it.
asking you
Okay, so
questions,
in
you want to
general,
know
I've seen
exactly
in
what they're
general.
asking you versus
So when you have a picture
assume.
that has
The
particles
amount
like
you're
this, go
seeing
ahead
is
and
the
track
amount
it.
left
Usually
over,
spend the time
right?
to
So it's
track the
4
changing
left,
amounts, and then
will
this is
give you an
4
idea of what is
left.
being discussed.
And then this
right?
one here,
In the beginning,
4
we have A,
got
we have B,
made,
right?
so you can
A
see
is
right
the
here.
blue tablet
1,
looking
2,
structures,
3, 4, 4 got
right?
made.
And then
So
B
4
reacted.
of both reactants reacted.
B
And then
is
4
the
got
red
made.
spheres,
Okay, let me
also
remove these
a
words from here because I
reactant,
feel like
right?
this
They're
is
kind of
less of
crowding
the
the
chemical
space.
reaction.
And then C is a product. So
Okay,
we expect,
so we're based on what we told.
talk about stoichiometry because
Reactant
it's simple. We have a 1-to-1 stoichiometry. What that means for
will
every, since
decrease.
the
That is
coefficient
what
in
they
our
mentioned
balanced
to
equation
us
is
at some
1,
point.
right? That's the expectation.
To
We're going
1.
into this with some
To
expectation.
1. Okay.
We also
This
know
means
for
product
every
one amount,
concentrations. I'm leaving the amount as general because the unit wasn't applied, right?
will
For every one
increase.
amount,
So
it can
we're
be
not
1
walking in
gram,
here
1
having
molar,
zero
1 mole.
expectations,
Not
one
in the world of
amount
science. You
of
walk in there with your hypotheses
that
and you're ready to
reacts,
change them as it fits, right? So we're going to
one
count. What I'm going
amount
to do here is
count and then mark this
of
off as I'm counting.
the
1, 2, 3, 4,
also
5, 6, 7, 8.
reacts.
I have
Okay,
8
this
A's in
part
this
is
picture.
important. So sometimes it's easier for
Here I
us to
have
skim
1,
through the
2, 3,
material
4. I
until
have
they ask you a
4
question. You're like, wait a minute, I
A's.
didn't cover that. So
And
you
then
want to
here I
make sure you
have
go through
1,
the
2,
stoichiometry because that
2
matters,
A's.
right?
And then
The
here I have
stoichiometry here is
0 A's.
communicating for every
Okay?
one
So we
amount,
know in the
whatever that
first
is, of A
reaction,
that reacts, one amount of B
before
also
any
reacts.
product gets made,
To
because we have T is
produce,
0, right?
time is at 0
One
before the
amount
reaction begins, because you usually start the time when the
of
reaction
C.
begins.
I
You
left
have the
the
maximum
unit
amount of
part
A possible,
general
which
because
shows
they didn't
here.
specify it. I'm
Oh, was
not
I
about
counting
to
the wrong
specify
thing?
it myself.
Okay.
Ah,
Now the amount can be molar amount,
I
it can
started
be
counting
moles, it can be
and I moved to the
grams, it
wrong
can be
thing.
whatever.
I kind of got
Okay.
distracted by that.
Now the time that
Okay,
has
I have to
passed,
be consistent, right, and count
35
the right thing.
seconds,
Right? How many do
right?
we have left?
I hate
The
this.
blues, 2 left. The reds, 2 left. Ooh, now I can't spell left. 2 left? Y'all excuse me, okay? I'm recording in the evening. And then here, how many do we have now? 1, 2, 3, 4, 5, 6. A total of 6 made. 6 aren't newly made. 2 additional ones got made, but now we have a total of 6 made, right? And then here at what, 50 seconds? Oh, 0 reactants. The reactants are gone. 0 reactants. And then 8 made. So here are reactants. You started off with stoichiometric amounts, so there's no excess reactants. Both ran out. Here we can say it's finally the end of reaction. And if you were asked this, you say reaction took 50 seconds to reach completion, right? And based on the reaction, of course, you can say if you want this from here to here, of course, 4 amounts of each reactant reacted, right? It wasn't always the same amount each time. From here to here, it was only 2 amounts reacted of each reactant. I'm trying to write lists, right? From here to get to 0, again, it was 2 amounts that reacted. And each time that the amount that reacted equal the amount that got made, right? Because it's a 1 to 1 mole ratio. Amount reacted. Okay, so this reaction is sort of fast. It got done. It's over in 50 seconds. When the reaction is over, we have 0 reactants. Let's see what's happening here. Now we got X, Y, Z. And the timing, oh, it's the same time. We got 0 seconds, 20 seconds, 35 seconds, 50 seconds, all estimated, right? So we start with the green. 1, 2, 3, 4, 5, 6, 7, 8. Once again, we have a 1 to 1 to 1 mole ratio scenario. So for every one reactant, every one of the other reactant reacts to form the product, right? So let's say, did I count 8? I thought I counted 8. 8 here, right, of the green. 1, 2, 3, 4, 5, 6, 7, 8. 8 of the blue, and then the product pink, 0. Nothing is made because the reactants haven't even gotten together, right? Now they get together, they have 20 seconds together to react. How much product do they make? Look at that. Just one. I mean, seriously, guys, you had 20 seconds. These other guys here had 20 seconds and they made 4 products. You can already see, right? If you're tracking or following the product alone, the first reaction is faster because in 20 seconds they made 4 products. Here they only made 1. It's going to be a long, long ride, right? To make one product, each one had to react. So we have 1, 2, 3, 4, 5, 6, 7. 7 left.
1, 2, 3, 4, 5, 6, 7. 7 left. It makes sense. Each one of each X and one of each Y had to react to make one of Z, right? It's the 1 to 1 to 1 mole ratio. Okay, here at 35 seconds, how many more Z's do we have? Well, there's 1, 2, so we have 2 total Z's. That means one more got made. You're like, geez, how slow is this? That's why it's a slower reaction, right? 1, 2, 3, 4, 5, 6. We got 6 left here. 1, 2, 3, 4, 5, 6. We got 6 left here. Once again, one of each reacts the reactant to form the product, right? So now we have this amount left over, this amount left over, and this is the product. Same time, now we have 50 seconds. Are we at the end of the reaction? No, because we still have reactants left over. We have 1, 2, 3, 4, 5. We have 5 reactants. So the first one, 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 of the second reactant, 1, 2, 3. 3 of the product. It's going to be a while before this reaction is over, right? So this is obviously a slow reaction. And this reaction has not ended. Why? Because we still have reactants. You have to keep going until your reactants zero out. Okay, now we're looking at defining reaction rates. So the first one here, I would argue this is defining the reaction rate by looking at a picture. So you want to make sure you know that. How to define rate from a model. How about that? The picture. This is a model. So make sure you know how to do this. I'm just telling you the type of questions, okay? When I was a student, I was thinking like a student, like stuff was happening to me and I had no control and I had to persevere and survive. At some point, I was like, no, I'm going to take back the power. Okay, I wasn't thinking like that, but I was like, you know what? I can anticipate what's coming. I went from feeling like stuff is happening to me in chemistry to thinking, wait a minute, I recognize this challenge. I've seen it before. And I said to see a pattern, right? So it got to a point where I said, seeing, oh, as we're working on this problem, I anticipate this kind of question being asked. I had a student that was so good at doing that. She would sit in class. That's when I was teaching organic chemistry years ago. Don't get any ideas. She will have her arms folded. And as soon as I taught something, she would look at me and almost in an accusation tone tell me, this is a good question for the exam. And I look at her like, I had just paused to think in my head, this is a good question for the exam. She looked at me and she said, it's going to be in the exam, isn't it? I was like, get out of my head. Anyway, the point was, while it took me a while to figure, well, it took me like up until first year of chemistry to figure out, right? So I guess we were kind of the same level as far as figuring out what kind of questions you see. So she was thinking, this is the kind of questions I expect to see in the exam. She was thinking like a teacher, right? She used to do so well in the exams because she could anticipate what was a good kind of question, right? So, yeah. When you see the questions as they're giving you examples, think about it. Is this a good kind of question based on the learning outcomes? If you can think that way, not just in chemistry, in any class, they kind of tell you what the questions are going to be from the learning outcomes and the goals. So when they tell you that, you can kind of anticipate, right, what those questions are going to be. Just think about it. Okay, so now we're talking about defining rate. We're defining rate now and going further into stoichiometry. Now we have a balanced equation. We're told here the rate of a chemical reaction is measured in terms of how much the concentration of a reactant decreases or the product concentration increases. Didn't we say this before? Yeah, we're saying it again. But now we're actually going to do something with it. For reactants, a negative sign is placed in front of the definition, like I did before, right? Only they're doing it. We now have a balanced equation. So let's see right here. In our balanced equation, we have two reactants, okay? There is this one, and then there is this one. Okay, so what I'm going to do, I'm going to erase this one here because once again, it helps when you get what they're trying to say to recognize when they have switched the focus. Okay, right here they're telling you for reactants a negative sign is placed in front of the definition. So here the definition is the same thing as the equation, right? They give you a rate equation. We had the balanced equation. In the balanced equation, while we had two reactants to pick from, They only decided to focus on I. So they're writing this rate equation, but from the point of view of I. I is the focus and I is the reactant. We know that reactants decrease in concentration with time. So reactant, I'm writing it again, concentration decreases with time. So for that reason, you have to have a negative sign. So I'm going to tell you right now, all rates in chemistry are positive. So let me write a little caveat here. All rates in chem are positive. Okay. So when you know that, it helps you. So just say you forgot, right? You're doing some kind of MCAT or something and you forgot. If you remember this and you get a negative rate, you're like, wait, why is my rate negative? Maybe all the answer choices are positive. You're trying to reconcile that logic. All rates in chemistry are positive. The chemicals are always reaction. They never, sorry, the chemicals are always reaction. They never de-react, right? So as you're making the product, if the rate is fast, then you have a large rate. So large rate equal fast reaction. Okay. Small rate equal slow reaction. Okay. So because the concentration of the reactant is decreasing, okay, I want to say right here, the reactant, let me call it R because writing the word reactant is just taking up a lot of space. We're going to do the reactant final concentration minus reactant initial concentration to figure out the difference. Once we subtract those two, since the concentration amount is decreasing, the final number will be smaller than the initial number, just in case you want to know. This would be a larger number. So when you take a small number minus a large number, you get a negative number. So negative times negative gives you positive. Okay? The difference, the change in concentration of the reactant concentration, think about that, is going to be negative. Negative times negative is positive. So we'll work this out so you can see. Okay, so where was I? We're right here, yep. And they picked this one here. And then when it comes to illustrating this, just like I did right now, they choose a different symbol. This kind of thing upsets me, okay? I'm like, we were talking about I though. How did you change to H? See, I'm not the only one who switches stuff, right? Sometimes my brain just switches stuff. It's like I'm bored with this letter. Can we go to a different one? They do that here too. I can't change this because it's a picture and I don't know how to get it to this exact format. So I leave it as is, but I talk about it. The rate of the chemical reaction over two time periods can be written as follows. So here they change the focus and the now we're looking at H2, the other reactant, not I2. But the idea is the same. It applies to both. The rate of the reaction is still a reaction, so it's negative. Change in the concentration of H2 over delta T. Now remember, 2 here, this is essentially final condition. 1 for the time is initial. Okay, this T2. So T2 is when the time that the time of the reaction is over, when the reaction has ended, or whatever you decide is the stopping point, that stopping point versus the starting point. So T1 is starting or the start of the reaction, and then T2 is the end of the reaction. So the end minus the beginning gives you that difference, right? Okay. So before we continued here, I wanted to introduce something before I forgot. Now, I realized that maybe I may have been a little premature because I wrote this earlier before I started teaching the actual lesson because I told you I had so many false starts today. Wait, how are these different? Okay, so let me go ahead and actually move this over. Wait, let me move this over. Wait, what happened? Oh no. Okay, hold on. I was here. I just wanted to have this move down. Okay, let me add a page down here. That's okay. I'll add this right here, and I'll deal with it when I get to it here. I'm trying to deal with this new. Yeah, I'm not gonna re-record this. I'm just gonna go with this, whatever. Okay, I'll write it myself. I can rewrite it because since I wrote the first one, I'm really struggling with all. They updated my app. It's not really, my app, but they updated the app, and so I'm struggling with the new changes 'cause I'm not very familiar with them. Anyways, let's look at the rate of the reaction and the stoichiometry and how it plays out. So we're being told here for these reactions, when you have a reaction where stoichiometry is a factor, the change in the number of molecules of one substance is a multiple of the change in the number of molecules of another substance. So here we're being told stoichiometry does matter to prevent the rate from being different. Wait, what? The rate can be different? Remember, I told you earlier, you can get to the same rate by tracking any reactant or any product. But if you don't take care of stoichiometry, you can have different rates. So it's saying here to prevent that from happening, the change in the concentration of each substance is multiplied by, there should be the word multiplied, is multiplied. I feel like there's a formatting issue here by 1 over the coefficient. Okay, so what they're trying to say here, let me go ahead and add a page. This should be simple, just add a page. And I'm going to move this over. Hopefully that will work out well since they have a new feature here. Copy this over. Now show you what they mean by this. Okay, remember, the goal here is to communicate. This is the goal. Rate can be calculated by tracking any chemical in the balanced equation. That's what they're trying to communicate here. Okay? So they did so by saying rate equal this and this and this and this. So let's go ahead and figure out our own rates. We'll figure out, since we have 4 chemicals, we'll figure out our rates. Okay? It's the same value of rate. Okay? Rate equal. According to them, they say that multiply each of the change in A over change in T by 1 over the coefficient. So I will do that. Rate, I'll start with the reactants. So I'll say here reactants. For my reactants in the balanced equation, my rate is, remember reactants, I'm going to write here to remind myself, decrease, therefore negative. The rate here will be rate equal negative, right? Because of the decrease part. You put a negative for decrease. And then you have a change in the concentration of the reactant. So I'm going to start with reactant A. Change in A over change in time. Okay? I can get the rate this way, or I can get the rate using the other one. Negative. I'll come back to the coefficient. I'm not done. Change in B over change in time. But if these coefficients are numbers that are not 1, then I have to multiply them here. Okay? So I have to multiply them here. Take this number times 1 over A, the coefficient of this. Here times 1 over B, the coefficient of this. So this becomes equal to negative 1 over A delta A over delta T. This becomes negative 1 over B delta B over delta T. Okay? So that's how I'm going to be dealing with the reactants. Now I'm going to be dealing with the product. I'm going to give a general term here where I bring in what I raised earlier. Okay? So over here, for my products, though, I got C and I got D. Okay. since I'm dealing with products are increasing. Increase. So remember, we're going to use a positive or leave it out. We're going to say here, rate equal change in concentration of the product. The first one was what? C? C over change in what? T. Second product, rate equal change in concentration of D over change in T. Now go back and look at your coefficients. C had a little c in front of it, so I got to multiply 1 over, right? That's what they said, times 1 over C, which is going to be 1 over C delta change in big C over delta T, okay? Times 1 over D, 1 over D delta change in D over delta T, okay? So these are my products. They're going to be positive. You can put a positive here if you want to. If it really bothers you, you can do that, okay? Okay, so here's the thing. You want to be familiar with problems and how scientists describe problems. The thing with chemistry, it's more in chemistry than it is in biology, if I recall biology correctly. With chemistry, sometimes they're asking you something you already know, but they're using different terminology. If you're not familiar with terminology because you didn't spend time to remember or memorize that, you have no idea what they're asking you. And I hear that a lot. Well, I have no idea what they're asking me. And I usually ask this question. When you were reading what they were saying before in the questions, were you rushing to answer it, or were you paying attention to how you were being asked? Right? You kind of have to learn how they're asking you things so you can know how to answer them. So one of the ways they're going to ask you this question here is, I have seen this, so I've made note of that. They can say in general, rate for the reactant equal negative 1 over the coefficient, right? Like we just saw, right? Times, you know how you have change of B over change of A? That's sometimes called the rate of disappearance. Okay, so I have seen questions where they're asking you, calculate the rate of disappearance. And I'm like, what? These words were never used, but they want you to understand reactants disappear as they decrease with time in the chemical reactions, while products appear. So you want to be aware of this alternate way of writing the rate of the reaction. 1 over coefficient times rate of appearance. Okay, you want to be prepped. So now you know if they ask you for this in this context here, your rate of appearance will be, of course, delta C over delta T, or delta D over delta T. Yeah, if they're asking you, they're really asking you for one of these. Appearance of the product. Over here, do I have room? This means delta, was it A, right? Over delta T, or delta B over delta T. So we'll work out a problem so you can see how it plays out. Remember, you guys are watching a recording, so feel free to rewind until it makes sense. Work out problems, that way you get the hang of when they're asking you stuff and how they're asking you. If they want just the regular rate of the overall reaction, they tend to say rate of the reaction. When they say stuff is appearing, stuff is disappearing, they want you to find the rate as it pertains or depends on the reactant. Only they have to tell you which if there is more than one reactant. Okay? So let's get to this question right here. Okay. Let me get some water. Okay. So it says here, consider this balanced chemical equation. So here we have a balanced chemical equation. Let me copy this. My stoichiometry right here. Oh, I got some room already? Okay. I got some room. Ready to go. Okay, here's my balanced equation. What are they saying? In the first 10 seconds of the reaction, in the first 10 seconds of the reaction, the concentration of I minus drops from 1.000 molar to 0.868 molar. Okay, that means if it's the first 10 seconds, that means the initial time was 0.0 seconds, okay? And then the final time is 10.0 seconds, right? When time was 0.0 second before anything happened, the concentration of I, so we're told I minus, right? Its concentration was this number right here. So I'm going to write this as 1.30, like that, right? And then it dropped to 0.868. I minus dropped to 0.868 molar. Now you can write this as IT1, IT2. I just write it as like 1 and 2, or initial and final. I don't want to complicate this, so I just say initial, final. Then maybe I can make this, like, I can be consistent here. How about that? Initial, final. Okay. Yep. What do they want us to do again? Calculate the average rate of this reaction in this time interval. So we want to figure out the average rate of this reaction in this time interval. Then what are they asking us next? Determine the rate of change in the concentration of H plus. Oh, they want us to figure out the rate of change, focusing only on H plus. So the question they're asking us here, the rate of change of H plus is the same thing as rate of disappearance of H plus. Okay, they could ask you this way like they asked, or they could ask you this way and you'd be solving for the same thing. Okay, so I'll redefine this when we're covering that part. Let me do the first one first. So remember rate, we're dealing with a reactant here. Oh, come on. I'm not stopping this time. Rate, we're dealing with I minus. I minus is a reactant. So let me pretend to forget the negative sign. I'll pretend to forget it. Okay. Change in I over change in T. I'm really trying to focus here. Okay, we're trying to figure out the rate of the reaction. They only gave us I minus, right? Remember the stoichiometry factors in here because you have different coefficients, so you have to include the 1 over 3, right? Times change in I over change in T. So this will be 1/3 change in I. Change in I will be the final minus the initial, so 0.868 minus 1.000. Remember, this is M over the final time, 10.0 seconds minus 0.0. This is seconds, right? I mean, you can put the M both sides if you want to. I just left this out here. Let me be consistent. It's the small things. Okay, there. So I'm going to forget the negative on purpose so you can realize that, remember, rate is always positive, so you're going to need the negative there. Just in case you forgot it, you just bring it back in. 0.868 minus 1. Oops. I haven't brought in the negative yet. I'm resisting the urge to do so. Negative 0.132 divided by 10, right? So we got M over S. So we got that number divided by 3 divided by 10, and I get this number right here. Okay, now if I forget the negative, I end up with negative 0.0044 meters per second. But remember, the overall rate of the reaction is always positive, so this has to be positive. So of course, to do it correctly, I should have had the negative here to begin with, and that's what will fix this and make this positive. So the rate of the reaction is this. That's the average rate. Okay, so just in case you forget it, remember the overall reaction rate is positive. It's only when you're dealing with a reactant only and they're trying to figure out how is that reactant changing with time. Only then do we have a negative and a positive value. Negative implying that concentration you're focusing on is decreasing with time. Okay, so here with this question here, the second one, determine the rate of change in the concentration of H plus. So we are trying to find H plus alone, not the whole reaction. Here it was the whole reaction. Here it's H plus alone. So H plus is a reactant, so we know it's going to decrease with time, right? They tell you that is delta H over delta T during this time interval. Here's the thing. I told you before, you can figure out the rate with any of those reactants, right? So we know from our balanced equation, what is the coefficient on H? It's going to be 2, okay? The same rate we just figured out is equal to negative, since H plus is a reactant, 1 over 2 times delta H, right, concentration, over change in time, okay? What do they want us to figure out? Delta H in concentration over change in time. Remember, delta H concentration over change in time is the same thing as rate of disappearance. I feel like I didn't spell this properly, y'all. Let's go back and do this right. Disappearance, yes, of H plus, or rate of change according to H plus. Okay, two different ways of saying it. They want you to solve for this. So trying to solve for this, remember we just solved for rate. Rate is up here. So we have this number. This rate is 0.00. Do I have it in my calculator? Yep. 44 meters. I'm not meters, sorry. This is molar per second. What was I thinking? Meters. Hold on. Let me rewrite. Oh no. Come on. I'm trying to get the positive version of my answer since I'm trying to make a point, and now I have the wrong version of my answer right there. Okay. 0.0044 molar per second equal negative 1/2 times the variable we're trying to solve for, right? Delta H over delta T, and this is the concentration of H. We're trying to solve for this. So go ahead and you can divide this by negative 1/2, divide this by negative 1/2, and let's see what we get. So take your number, I'm going to divide mine by negative, open parentheses, 1 over 2, close parentheses, and I get this as negative 0.0088 molar per second. This is the rate at which delta, the H plus concentration, oh, I forgot the plus is right here, is changing with time. So in the same 10 seconds, this is the amount of H plus that reacted, okay? It decreased by that amount. So this is kind of how you can tell each of those reactants. Imagine you giving a shape, right? This is a, say, a square, and this is a triangle, and this is a circle. You can show after 10 seconds, the circle amount should be less by this amount right here. Okay, and they told you the amount. Yeah, you should be able to figure out the amount by which I minus will also be less, which we didn't really work it out that way, but you can just do the change in this, right, over time here. Subtract these two, divide by 10. So it should be, looking at this right here, it should be like 0.0132. So the amounts don't matter. I mean, sorry, they shouldn't say they don't matter. They don't match. Sorry, they don't match, right? The rate at which I minus reacts doesn't match with the rate at which H plus reacts because they have different coefficients, right? Probably have different starting amounts. Okay, anyway, hopefully you've seen that. They work it out, they get this, they have scientific notation, everything is written that way. They work it out, they get this one too. So you want to be aware of how to figure out these problems and solve them. Okay, they do have this one here. Oh, you can predict the rate of change of the following right here. You can go ahead and do that. If you have questions about this and you want me to work more of it, let me know. I'm trying to work on a deadline here. So I'm going to end with this, finding the rate law using the initial rate method. Since I found out while I was doing my 7th take that we're not going to be having class tomorrow, then what I'm going to do is continue to record this privately and then post it. And whenever you can watch it, you can watch it. Okay. So there's something called a rate law. So before we try to find it, what is the rate law? What we've seen so far is figuring out the rate from either tracing or tracking the product or the reactant. There's something called the rate law. And I call the rate law, I say the rate law is similar to the point slope form equation of the line. You know the point slope form equation of the line where you have y is equal to mx plus b. It's not equal in purpose, but it's equal in the style. When you look on the format, I would say, when you look at the way this equation is written, some parts of the equations are variables, some parts of the equations are constant. So when you look at the equation of the line, the point slope form, the y and the x are variables, so they're left as a variable symbol. You leave the y and the x as a symbol. Then m and b, because they're constant, you write those in there. In the rate law is technically an equation. And it's an equation that communicates something. The rate law communicates the effect of each reactant on the rate of reaction. I try to simplify my definition and I only complicate it when, well, I shouldn't say I wish. I complicate it when I have to add more information, right? So let's start with simple. We're going to always add to it. The rate law is an equation. So I'll say here, an equation, and it has a purpose, right? What does it do? It communicates the effect of each reactant on the rate of the reaction. So going back to what we just experienced, apparently the reactants can change in different amounts in the same given time if the coefficient is different. So you can say that each reactant can influence the rate differently. That's a possibility, right? The rate law is not a law that says, well, when this happens, that happens. It's not that kind of law. It's an equation that communicates the behavior of each reactant and its effect on the overall rate of the reaction. Okay. So, oh, by the way, I forgot to mention this. From here on, we are now focusing on reactants only. This shit has happened. We are focusing on reactants only from here on. Okay. So as we're looking at this, hold on a second. I feel like there's a page that got missing because I was trying to show you guys something and there's a page with the graph. As I was scrolling through, this graph right here. I need to communicate something important, so I don't know how it just got missing. With this new page, this new app or the updated version, some parts of it is super sensitive, some other parts of it is just, yeah. So before I move over to this, I need to talk about, hold on, paste. Okay, let me delete this page here. Okay, so we're right here. Okay, before we start focusing on the single reactant, we want to look at the graph. You want to be able to interpret. So we're talking about interpreting the graph. Okay, one of those learning objectives written in the syllabus that you need to know how to read the graph. Okay, we want to know how to interpret the reactant and the product concentration changes as a function of time. How is the reactant concentration changing with time? How is the product concentration changing with time? So as we look at this table here, this graph, our focus is to answer those two questions. How does reactant concentration change with time? And we're doing the same thing for the product. How does product concentration change with time? Okay. So as I look at this here, this is the last time when we're focusing on both. From here on, remember, we're focusing on reactants only. This picture, by the way, this graph here, is illustrating what is going on in this balanced equation that we saw earlier. Now, they chose to focus on one reactant only, right? Because I recognize, even though we have two reactants, H2 and I2, they chose H2 for whatever reason. That's what's being featured here. They could choose both and they'll use a different color for I2. They chose H2 only. And then for our product, we only have one product. It's right here. So here's the bottom line. They're communicating that at time 0, the x-axis is time in seconds. We go from 0 to 120 seconds. Yeah, in seconds, right? And then concentration, we go from 0 to 1.8 molar concentration. That's your y-axis. Okay, so I'm going to trace or track the amount of my reactant H2. In the beginning of time of the reaction, before anything takes place, we have the maximum amount of the reactant possible. I would say maybe around 1 molar, right? Around 1 molar. And then the reaction takes place. As time goes by, the concentration of the reactant concentration decreases, right? A little bit reacts, it starts reacting. So we're only tracking the amount that's left over, not the amount that's reacting. The one left over decreases until the reaction ends, where this drops to 0, right? Meanwhile, in the beginning of the reaction, there's no product. It begins to get made and made and made, and then a lot of it gets made, and it keeps getting made until either one reactant runs out, the limiting reagent, or both run out and the reaction ends. Eventually, this will flatten out because you make the maximum product possible. Eventually, this will deaden out because you run out and it'll be over. The reaction will just end. Okay, so this picture shows you both the product behavior right here, and then the reactant behavior right here. I remember years, just so many years ago, when we were asked to sketch these things. So you have to understand it to be able to sketch it, right? Reactant concentration decreases with time until it ends. Product concentration increases with time until it ends. So you want to be aware of that. Okay, back to what I was talking about right here. Now that we're talking about the purpose of the rate law, remember, it says right here, before we get into it, we have like a warning sign, warning. Rate law must, this is a must here, must be determined experimentally. Now, we will use calculations, but there will be a data table provided. Data table from experiment provided. Okay, so don't check out and say, well, I don't have time to do experiments, so I can't do this. No, all they mean is you have to use a data table that came from an experiment, and then from there you can figure out the rate law. That's an equation, right? The rate law shows how the rate of a reaction will change if we change the concentration of either reactant, assuming there's more than one reactant, right? How each reactant's concentration change influences the rate of the reaction. Changing the initial concentration of a reactant will therefore affect the initial rate of the reaction. Okay, so let's go ahead and see an example of how this plays out. The rate law, the effect of concentration on reaction rate. The rate law of a reaction is a mathematical relationship between the rate of the reaction and the concentrations of the reactants and homogeneous catalysts as well. So bottom line, this is a generic form of the rate law. So when they ask you for rate law, the answer you're looking for is something that looks like that, but that's the generic form. So you tend to adapt it to the question they gave you, right? So I'm going to tell you this. The term rate remains as the word rate. So, right, rate. Leave it as rate. And then when you're asked to provide the rate law, leave as K. There's only two parts here that get replaced. A replace with, I need space, formula, right? The chemical formula. And then N is replaced with a number. So rate and K are left as is. N replaced with number. Like I was saying earlier, it's kind of like the point slope form of a line, the equation of a line, where some parts of variables are left as is. So the rate in this case here is left as the word rate, and then K is left as the word, as the symbol K. Okay. So what I mean by that is, in general, we're being told based on this equation right here, the rate of the reaction is directly proportional to the concentration of each reactant raised to a power. Sometimes they use this definition here to define the rate law, what it is. So the other definition we looked at before was more about what it does, or what it is important for. This one here is more like what it is, or what it symbolizes, what it shows, right? It shows here the rate of the reaction is directly proportional to the concentration of each reactant raised to a power. So let's go ahead and apply it. We have a balanced equation here, A with a coefficient of A plus B, coefficient of B, to form products. So one of the things chemists do is they focus and they kind of, I don't want to say fixate, but let's look at it like fixation. They fixate on reactants in this section right here. Since we are fixating on the reactant and ignoring the product, even though they are formed, we just leave product as the word product to communicate that we are only focusing on the reactant. Okay? So you're told, when you're given an example like this where A and B are reacting to form a product, if you were asked to write the rate law, you will write it like this. The rate law, okay, will be written like this. Rate, the word rate, equal K. The brackets represent concentration of A is a chemical, the reactant, raised to the power M. B, the other reactant, raised to the power N. They were sure to write the coefficients here as A and B, and the powers as M and N, just to let you know that M is not equal to A and N is not equal to B. So what are they trying to communicate? They're trying to say that these powers you're going to have in the rate law are not the coefficient from the balanced equation. Okay, so M did not come from the balanced equation. N did not come from the balanced equation. They came from somewhere else. Okay. Once again, guys, feel free to rewind. So let's go ahead and actually get to a real question where we have data from experiments. Here we're told, determine the order and the rate constant of the reaction. So one thing I want to do is, because I don't know, I feel like a lot of slides were skipped for some reason. I want to go ahead and define what the order of reaction is. M and N are actually called orders of reaction. Okay, so let me go ahead and add a page here and define that. Since M and N are not coefficients, M and N are not coefficients from the balance equation. No, they're not. But they are called order of reaction. M shows how reactant A affects the rate of reaction. and N shows how reactant B affects the rate of reaction. So they are not the coefficient of the balanced equation. They have a purpose, and that's to communicate how these reactants here influence the rate of the reaction. Okay. Once again, as you watch this video, if you have questions, write them down, shoot it to me in an email. We can't have traditional class because y'all probably got the message school is out till Monday. But I don't want you guys to fall behind because time will not be generated, right? So, yeah. Okay. So here it says determine the order. In other words, since we have two chemicals here, M and N, find M and N. I have to say, and the rate constant of the reaction. Okay. So as we're looking at this here, it says NO2 plus CO form NO plus CO2. So this consider the reaction between nitrogen dioxide and carbon monoxide. So we have these two. The initial rate of the reaction is measured at several concentrations of the reactants with the results shown in the table from the data table. Where's the table? Oh, all the way down here. I need that table. Oh, okay. What I'm going to do, since the table is all the way down here, let me copy the table. I need that to solve the problems. Okay, so let's pretend it's up here, like I just moved it right here, because I need that to do my work. Okay. So initial rate of the reaction is measured at several different concentrations of the reactants with the results shown in the table. From the data, determine the rate law for the reaction. Remember, rate law has the format rate equal K, open parentheses, reactant, raised to the power M. Repeat this for all the reactants you have. And then after we do all that, they say the rate constant. Oh, solve for this K. What is K equal to? Okay, I can do that. Okay, so here's my thing. I'm going to be figuring out the rate law. Let me not be lazy. Since I have two reactants, I'm going to have two reactions in my rate law, right? That's what I think. I'm hypothesizing. It will look like this. Rate equal K, and then I'll have my first reactant. So I'm writing a little slow, smaller, raised to the power M. Second reactant, I should call it reactant 2. Reactant 1 raised to the power M. Second reactant 2 raised to the power N. It will look more like this. Of course, I'll go in there and write what the reactants are. I will solve for M and N, and that will help me complete my rate law. After I'm done doing all that, I will solve for the rate constant like they're asking for, which is K, the symbol K in all of this. Okay? Well, how do we solve for M and N? Here's the thing. To solve for M. Let's start with M. I will write my rate law. Okay. I need my balanced equation though. Let me copy this over. I'm so used to recognizing my symbols by how they look. Now I have to remind myself it looks different. It looks different. Wait, I already copied this, didn't I? Copy. Oh, come on. Okay. Yeah. So I'm trying to solve for M. So what you're going to do here, to solve for M, you're going to be using the rate law, right? You will write the rate law for each experiment. So here we have 4 experiments, 1, 2, 3, 4. You will pick 2 out of the 4 experiments that have a certain criteria. And then you write a rate law for them and then work things out. So to solve for M, I'm trying to solve for M. First of all, I need to write a mock rate law. My rate law will look something like this, okay? So this is my presumptuous rate law. My rate law will look like this. Rate equal K. My first reactant is NO2. NO2 raised to the power M. The other one will be CO raised to the power of n. So I know my rate law is going to look like this. I'm going to solve for m. I'm going to solve for n. And when I solve for those, that completes my rate law, right? So to solve for m, I'm starting with this part here first. To solve for m, I have to pick two experiments. Those two experiments, since I'm trying to solve for m, I want to keep CO constant. I want to keep CO from influencing the observations I'm having. So to solve for m, which goes with the formula NO2, right? Keep CO concentration constant. That's the goal here. So select two experiments in which the concentration of CO is not changing. This is our goal right here. Pick two experiments. So I'm going to write what I'm doing here. Pick two experiments in which concentration of CO doesn't change. Okay? CO. 0.1, 0.1 doesn't change. Will that work? Sure. So I'm going to pick experiment 1 and experiment 2. And for our purposes, I'm just going to give a shortcut. I like the big numbers on top. So I'm going to work here and say experiment 2 divided by experiment 1. Okay? So write your rate law. So in other words, I'm going to do rate 2 over rate 1 equal K NO2 M. Oh, let me actually work this out and plug in the numbers so it'd be a lot quicker because I feel like I'm just going on and on. So let me go ahead and work this out so it'd be a lot quicker. Okay, what's rate 2? This is the initial rate. This is the number I need right here. Rate 2, 0.0082. Here, 0.0082. What are my units? Molar per second. Molar per second divided by equal K. So I wrote this rate part, right? And I wrote this K part, okay? And over here, I need to write the NO2 part. What is the NO2 for experiment 2? Because this is experiment 2, right? NO2 for experiment 2 is what? 0.2. 0.20 M. And then this is going to be raised to the power M. I have no idea what M is. And then for CO experiment 2, that's going to be 0.10 raised to the power N, right? All of these are information about experiment 2. Divide that by information about experiment 1, starting with my rate. So I have to start with rate for experiment 1. What is that? 0.021. Wait, is it 0.021 or 0.0021? You need to copy those correctly. Don't be like me. Do better than me. Go out there and do better. 0.0021, also molar per second. I don't know what K is, but K is part of that rate law. So essentially, I'm writing the rate law for experiment 2 over rate law for experiment 1, just in case you're wondering, okay? For experiment 1, my NO2 concentration is what? 0.10 molar raised to the power m. This is the same thing, right? For CO, we kept CO constant, so it's going to be the same number, 0.10 raised to the power n. Okay, so we take rate law 2. I guess I should write this like rate law 2, right? Rate law 2 over rate law 1. That's what I did here. Units cancel out, K's cancel out, this cancels out. Look at how much it makes our math simple, right? Because chemists are like, listen, life is already tough enough. Why should we make our math any more difficult? So I got a 3.90. I divided these already. 5 equal 0.20. Oh, the m's in here cancel out. Power m over 0.10 power m. So there is a rule in math that says when you have numbers with the same exponents, you can consolidate them, right? So we're going to consolidate these two. They become 0.20 divided by 0.10. And then the exponent applies to the numbers, the base numbers, 3.905. Now this ends up being 2 power m. And then this number is close to 4. You can round up to 4. Now the way the book works it out, they use logarithms. You can do that, but that's junior level is where you need to do all that stuff. I think at you guys level you can coast without doing the log. Essentially you do the log of 4 divided by log of 2, all that stuff, and then you get your answer. You can do that if you want. They show it out in the book. I'll show you how they work it out. I like doing the exponent form is a lot quicker. Okay, this here you want to write 4 as a number of base 2 where the value is the same. So 2 power 2 is equal to 4. You want to rewrite it, the number where the base is 2, and then 2 power m. So if the base numbers are the same, the exponents are equal to each other. The base numbers are equal, the exponents are equal, therefore m is equal to 2. Okay, we just solved for m. Now that we have m, we can do the same math, but this time we're doing it to solve for n. To solve for n, we have to keep NO2 constant. To solve for n, keep NO2 concentration constant. So our goal here in picking our experiments is with that in mind. You want to keep NO2 concentration constant. This is the logic behind it. If you're a logical thinker, you would appreciate the logic. When you're doing scientific experiment, you don't want to have too many variables, too many things changing. That way, if you change one thing, if you stick with changing just one thing, you can tell the change in the results is due to that one thing. If you have more than one thing changing at the same time, how do you know what was the one that gave the results? You don't know. You're going to just speculate away. So here we're changing. If we're keeping NO2 constant, we're only changing CO. So whatever change in the experiment we have is due to CO. Then we can tell how CO influences the rate of the reaction, right? So now I'm going back here. This is so far away now. Let me copy this over because I'm struggling with scrolling back and forth. My eyes from looking at the screen this whole time. Okay. So, hold on a second. Let me move this over here. Now, oh, I can't even erase because that's the picture now. Okay, sorry. Okay, so now I have to look for an experiment. Hold on a second. My eyes are really burning. We're going to be looking at an experiment this time in which NO2 is kept constant, right? You probably can figure that out. Hold on. Ooh, okay. After this, I'm done. I need to give my eyes a rest. I'll watch the TV screen instead. It's a little far away from my eyes. Okay, so experiment 2 and 3, right? NO2 is constant. So we're going to be doing 2 and 3. 2 and 3, which is bigger. The numbers in 2, this is bigger than that. So we're pretty much going to be doing experiment 3 over experiment 2. And let's see, we're going to do rate law for experiment 3 over rate law for experiment 2, right? So we start with the rate, which is 0.0083 molar per second over 0.0082 molar per second equal K over K, concentration of NO2 raised to the power. Since we already know what the order on NO2 is, what was it? 2, right? So you can write it here. Go ahead and write it in because it helps you with other problems. NO2. Oh, I'm supposed to write the actual numbers. Focus. It's towards the end, right? I'm already thinking about what I'm going to be doing. Let me focus on this. NO2 is supposed to be what? 0.20 raised to the power 2. Here it's still 0.20 raised to the power 2. Now we're looking at CO. CO is supposed to be 0.20 raised to the power N. We have no idea what the order is. This is 0.10 raised to the power N. Right? We're trying to solve for what is N. Okay, now that we have all experiment 3 stuff on top, 2 on the bottom, we can work this out. This and this cancels out. The units cancel out. This cancels out with that. Even though we have it solved, it still cancels out. Now I'm going to divide these two numbers. It comes up to 1, y'all see. It's so close to 1, right? So now I'm left with 0.20 raised to the power n over 0.10 raised to the power n. I'm going to consolidate this and get 0.20 divided by 0.10 raised to the power n. What are we dealing with here? This is 2, right? Divide these 2 raised to the power n, and we got 1. Now we have to rewrite the number 1 raised to the power, we have to rewrite the number 1 having a base of 2. So go back to your math rules. Any number power 0 is equal to 1. So 2 power 0 is equal to 1, right? Because any number power 0 is 1. So we want the number to have a base of 2. So 2 power 0 equal 1. That replaces 1. 2 power n. So then if the bases are the same, so are the exponents, right? So n is equal to 0. Okay. Have we answered the question yet? No. All we did was figure out the orders of the reaction. So what does this mean, by the way? What do these orders mean? Let me write the rate law, and then I'll tell you what it means. Now that I have these, I can write my rate law. The rate law is equal to the following. I'll write it as rate equal, you remember, you leave the word rate as rate, K, open parentheses, NO2, open bracket, NO2, close bracket, raised to the power 2, and then CO raised to the power 0. Remember we said anything raised to the power 0 is 1. So the rate law is really rate equal K NO2 2. This is the answer. This is our rate law. Okay? Okay, what does this mean? You need to know the implications of this. This means that, meaning, when NO2 concentration doubles, the reaction rate quadruples. Because it's squared, right? So it quadruples. It doesn't also double, it quadruples. If it was first order, it will actually double. It quadruples. When CO concentration doubles, the rate of reaction does not change. You're wondering, why doesn't it change? Because it's a 0 order. 0 order just means the reaction rate does not change according to the reaction rate does not change in response to changing that chemical. So say, for example, to kind of make this more relative, if you were in a company and you were working on this reaction and your boss said, make the reaction go faster, your best bet is to change the concentration of NO2, because anything you do to that, you square it and you get the change in the rate law. If you double this, this quadruples. If you triple this, square that, you get the rate. That's how it influences the rate, right? The double and the quadrupling is a lot easier for me to say. Whatever number you put in here, whatever change you do to NO2, you have a significant change with the rate. But since CO doesn't even appear in the finalized rate law, If you try to double this, you're wasting chemicals and you're wasting the company's money. Okay? When you're working for a company, you're trying to get a bonus so you can get your ride or whatever it is you want, vacation. I don't know what your goals are, right? I don't know. I know what my goals are. That vacation, that ride, that purse. Yeah. So this one here, if you try to change the concentration of that, you will not be influencing the rate, so you just be wasting chemicals. So you want to know that. Now, is this chemical important? Yeah, without it, the reaction won't take place. But is it important in making the reaction go fast? No, it's not, because it's a zero order chemical. Okay? So hopefully you understand that. Now that I've said all those words, what was the other part they wanted us to do? They wanted us to find K. And then we're done. Well, for tonight. Just for tonight, y'all. Just for tonight. Okay. So after all that, I know rate law is equal to K NO2 raised to the power 2. There's no CO in the final rate law. Now they said solve for K. That was the second part, right? You have 4 experiments to pick from to get your numbers. Pick any 4. I tend to like the easiest one, which is the first one. So I would say I will using experiment 1. You can use any of the experiments provided. I'm going to use experiment 1. For experiment 1, I'm going to use these numbers right here. So my rate is the number on the right, 0.0021. Don't forget the units. Units matter in chemistry. Molar per second equal to K. We're trying to solve for K. What's the concentration of NO2? NO2 is 0.10. 0.10 squared. Okay. Okay, where was I? I guess I could divide. Oh, I'm a hypocrite. I know I just said units matter and then I forgot it. Listen, I'm constantly judging myself anyway, so like there. Okay, because I'm like, where are the units? Divide by 0.10 molar squared, divide by 0.10 molar squared. Okay, so this cancels out, so we're left with K. So this is going to be 0.0021 molar per second. Let me square the bottom part. 0.1, where's my square? Square. The number squares and gives us 0.01, and then the unit becomes m squared, right? Don't forget you're squaring the unit and the number. So one of the m's cancel out with the top m's. We're left with one m. So the number, as far as the number is concerned, we have 0.0021 divided by 0.01, and we end up with 0.21. 0.21 1 over molar second. This is K. You can look at it this way, or it can be written as 0.21 m power negative 1 s power negative 1, and this is going to be K. Mathematically, these units are alike, right? If you don't like fractional units, you can bring the denominator on top, but you raise it to the power negative 1. I don't know the math rules right now. Okay. So they go ahead and they work it out. They use a very different method. It's a more direct method on how to get the orders of reaction. You can see that. It shows you here. NO2 has a second, they call it second order. Second order. This one here is called zeroth order. So when you have a zero order reaction or zero order reactant, it's sometimes called zeroth order. I don't know why they named it that. That's what they named it, zero order. When we go through the whole reaction, they show you different ways. You have the exponent form, then you have the log form. The exponent form was the one that was up here. I used that one by approximating this into 4. They have the log form right here where they do all that, and then in the end they approximate. I'm like, why do all the logarithm stuff and then still approximate, right? And then they work this out. They do all this and they get the final answer for they are the value of K. Okay. If you have any questions about this, please send me email before I do my recording for tomorrow so I can go ahead and actually address this. I'll try to do my recording whenever it's convenient based on what's going on right here. So it might happen in the around 11, maybe not. Just let me know. If you would rather join me in the lecture tomorrow, let me know so I can have a set time because I'm aware you're coming in. Okay. Other than that, y'all have a nice evening. Okay, so I'll end right here.